Hi, this is Mrs. Brunk. In this part of the lesson, we are going to be looking at writing absolute value functions from a graph. So we've been talking about this, what's called vertex form of an absolute value function, and we know that each of the parameters that we add to the absolute value of x has some sort of effect, either vertically or horizontally, on the shape, on the position, the direction of the graph. And so we can use that same information if we have a graph, so we already know whether it's been translated or whether it's been stretched or compressed or reflected, if we wanted to then take that information and write a function that describes the graph. Now we talked a little bit about how, in the exploration, about how sometimes, how a vertical stretch could also look like a horizontal compression. And so that's something we're going to keep in mind when we don't know exactly what's been done. We might assume it's a vertical stretch. It could be a horizontal compression, or vice versa. Could be a horizontal stretch and a vertical compression. And so we usually have to make some assumptions. And in this example, we're going to assume that there has been no vertical stretch or compression. We're going to say that the A is equal to 1. And we're going to assume that because this thing has obviously been stretched or compressed, that it must be something horizontal. So it looks like it's been a horizontal stretch. And so we're going to see if we can, in fact, figure out what stretch has occurred. Because other than that, we know what this equation is going to look like. We know that because the coordinate is 2, 5, that h is going to be 2, and we know that k is going to be 5. And so we kind of have a start to that. And so this is how we might go about finding what that actual b is. So step 1 is we're going to go ahead and take the standard form, and we're going to plug those values in. And so I'm going to go ahead and plug 2 and 5 in for h and k. And I'm also going to plug in the 1 for a, which really means I'm just not going to put anything out in front of the absolute value because putting 1 out there is the same. Now, in order to find out what that b is, I'm going to have to know more information because I can only have one variable in an equation. And so I actually do know some more information. I know this point that's also on the graph at 6, 6, and that represents an x and a y coordinate. And so I'm going to go ahead and plug those values into the equation as well. So in place of g of x, which is really like saying y, I'm going to plug in the y coordinate, which in this case the y and the x are the same. That won't always be the case, so be sure that you put the x in for the x and the y in for the y. And then I'm going to go ahead and plug in 6 for x as well. And so then it would look like this. And I, of course, still have my vertex in there. And now I'm going to clean that up and see if I can solve and find out what b is. So 6 minus 2, following order of operations, 6 minus 2 is 4. I'm sorry, I wrote that as 1 over 6. That was an error. That actually was supposed to be a b, but I just can't read my own handwriting. And so, anyway, that 6 minus 2 is 4. 4 times 1 over b is 4 over b. But then we have this plus 5 off the end. So now in order to solve for b, the first thing we're going to want to do is subtract the 5 from both sides, which leaves us with 1 over here, and then the absolute value of 4 over b. Which in this case you can kind of just think about solving for b kind of just mentally. 4 divided by what would give us an absolute value of 1? Well, there's two different things it could possibly be. b could be 4, or b could be negative 4. But if, say, this wasn't as easy to figure out, you could then consider the two possibilities. Either 4 over b could equal 1, or 4 over b could equal negative 1. Because the absolute value would take care of the negative part. So using the cross products, we could see that b could be 4, or b could be negative 4. Now the reason why I'm going to eliminate the possibility of it being a negative 4 is because, I'm going to cross this one out, is because you can see this graph has not been reflected over the y-axis. And so we're going to go with b is equal to 4, and now we can write our official equation like this. So then we can write our equation as g of x is equal to absolute value of 4 times x minus 2 plus 5. So you can clearly see the slide, 2 units to the right, 5 units up, and you can see that in this case, this was a stretch horizontally. Oh, I'm sorry. There you go. Should be 1/4 because we were finding our B, our stretched horizontally of factor 4. And I know sometimes that looks tricky because we have a 1/4 there, but remember it's 1 over B. So B is 4 in this case, and that causes a horizontal stretch of factor 4. And if you think about having a slope of 1/4 of absolute value branches, it would actually look like that it has been compressed vertically. But in fact, it's been stretched horizontally because we said that A was equal to 1, so we were assuming that this whole effect was due to a horizontal stretch. So that will be our final equation for this function. Let's go ahead and try another one. Now this time we have a graph that's facing down, and we can see that its vertex is at 1, 6. And we're going to assume, we can tell there's something going on here widthwise, so it's either been compressed horizontally or maybe it's been stretched vertically on top of this whole reflection. But this time we're going to assume, and you kind of have to do this, you just have to assume one or the other. Either you think it's vertical stretch or compression, or you say it's horizontal. And because we're going to just say that the B is equal to 1, so basically what we're saying is there's no horizontal stretch or compression. This will all be vertical. So we're going to start off the same way, and you can see that we kind of walk you through the process a little bit. Step 1 is to go ahead and take that vertex and plug that in for your H and your K. So the H coordinate of the vertex is the 1, and so we're going to plug that in. And the K, or the Y coordinate of the vertex, is 6, so this is slid 1 to the right and 6 up. So we're going to plug those in. And then what we're also going to do is take a point that's on the graph. So you can see that there's another point identified right here, 0, 3. And so we're going to take that x and y coordinate. We're going to go ahead and substitute it into the function. So in place of g of x, we're going to put the y, which is 3. And in place of the x here, we're going to plug in a 0. And now we're just going to go ahead and simplify this and solve it. So step 1 is to do the absolute value. 0 minus 1 is -1. The absolute value of -1 is 1. Multiply that by a, that's just a. And so then what we could do is go ahead and subtract that 6 from both sides. And if we subtracted that 6 from the 3, that makes this -3. And what that says is then that a must be -3. And so now we know exactly what kind of vertical stretch or compression it is. It's actually a stretch of 3, and the negative makes it a reflection down. So it also will tell us, this process will tell us, as far as whether it was reflection or not, because we can obviously see in the graph that it is. And so our function then would look like this. G of x is equal to -3 times the absolute value of x minus 1 plus 6. And we could graph that in our graphing calculator to verify that, in fact, the graph looks like the one here. We're going to go ahead and do a you try question. And so I'm going to go ahead and have you try in your notes your turn number 3. And I'm going to have you pause the video. So go ahead and give it a try. And then once you're done, tune back in and check your answer. Go ahead and pause now. Now I chose the easier route, and so I chose to make B equal to 1 so that I had to find A. That tends to be the easier way to do it, and because obviously I made an error on the last one. And so the way that I did it was I went ahead and found the vertex, which is at -5, -1. And then I substituted that in along with one of the points I identified on the graph. Now I happened to identify -2, 5. It didn't really matter which point as long as you were able to locate a point that looked like it was on some nice integer values. I substituted those in and I solved for A. And I found out that A was 2. And so this was the function that I wrote. Now had I chose to say that A was 1, in other words, that this was a horizontal transformation of some sort of stretch or compression, then that would have actually made the B be equal to a half. So if I found the B instead, the B would have been a half, because then 1 over 1/2 is 2. And so the alternate version of this equation could be this. And again, this 2 comes from the fact that that would have been 1 over the B, and the B is a half, and 1 over 1/2 is equal to 2. Okay? So that's why, in effect, with these absolute value graphs, it doesn't really matter whether the 2 is inside or outside. It has the same effect on the graph, and that really is to make it look like it's stretched vertically or compressed horizontally, which has the same effect. Now the final thing we're going to do is we're going to take a look at modeling with absolute value functions. So we're going to kind of look at, like, if we could take a real life situation and we could write a absolute value function that would model perhaps say like the path of a bounced ball or a beam of light or something like that. So light travels in a straight line and can be modeled by a linear function. When light is reflected off a mirror, it travels in a straight line in a different direction. From physics, the angle at which the light ray comes in is equal to the angle at which it's reflected away. And that angle coming in is actually called the angle of incidence, and the one that's going away is the angle of reflection. And according to physics, they would be equal. So we're going to take a look at a problem, and we're going to see if we can use this concept and the idea of absolute value to write an equation to describe and model a real life situation. So at a science museum exhibit, a beam of light originates at a point 10 feet off the floor. It is reflected off a mirror on the floor that is 15 feet from the wall. The light originates from: how high off the floor on the opposite wall does the light hit if the other wall is 8.5 feet from the mirror? So because the angle of incidence and the angle of reflection are the same, this creates basically a piece of an absolute value graph. And the vertex of this absolute value graph we could identify as being 15, 0, because it's hitting the ground, which means it's at height 0, and it's 15 feet away from the wall. So that's the 15 for the x and the 0 for the y. Now, in order to write an equation, we also need to know another point. And so this other point we could use is just the one that's at 0, 10. And that's because at the start, it was 0 feet away from the wall, and it started 10 feet up on the wall. So we have the point 0, 10 that we could use then to, along with the vertex, to find out what the A or the B is, depending on whether we think this is a vertical compression or a horizontal stretch. So I'm going to move on to another slide just to give myself room to work, but we'll come back and look at this picture, and I'm going to write down the two key points: the vertex, which is at 15, 0, and then we have this other point at 0, 10. So we're going to go ahead and do the easy way, and we're going to say that we think that this is not a horizontal stretch or compression, but that the B is 1. And we'll focus on finding a vertical compression that will help us describe the path. So step 1 is we're going to go ahead and plug in the vertex and this point. So this is the x and the y coordinate of the other point, and of course this is my h and my k of my vertex. And so when I go to plug that back in, it will look like this. 10, which is the y coordinate, is equal to, and I know I'm going to try to find an a, so I have an a in my equation, absolute value of the x, which is 0, minus my h, which is 15, and then plus the k, which is 0. So then we have 10 is equal to, and we simplify this, 0 minus 15 is negative 15. The absolute value of negative 15 is 15. So that's 15a, and then plus 0, so that 0, does nothing, basically we can just kind of eliminate it right there. And we know then that in order to find out what a is, we just have to divide both sides by 15. And if I divide both sides by 15 and I reduce it, I'll get 2/3. And so we can say that A is 2/3, and that means then we can write this function that describes this path over here on that prior page. It describes that path. We've got, this is my vertex. We found out that A is 2/3, and we can write it like this. It would be g of x is equal to 2/3 absolute value of x minus 15 plus 0. Now that 0 is not necessary. You could leave that off because there is no slide up or down. It's right on the floor. So now the point of why we wrote this equation is so then we can, if we wanted to actually use the function to find out how high up on the wall this is actually hitting, now we can just simply go ahead and plug in whatever that x coordinate is in for x, and then we can find out the output, which is the height. So this x coordinate now is this whole length, which is 23.5. If we had 15 and 8.5, so if we were to plug in 23.5 into that equation, it would look like this. It would be 2/3 times the absolute value of 23.5 minus 15. So let's see, 23.5 minus 15 is 8.5, and 8.5, absolute value is 8.5, times 2/3 would be approximately 5.67 feet. And that makes perfect sense if you look at the scenario that this is going to bounce up a little lower, quite a bit lower actually, on the wall, opposite wall, because it hasn't had a chance to travel horizontally that full 15 feet that it needs to. And so it hits the wall at about 5.67 feet. So even though the numbers are not quite as convenient on a problem like this, it really is the exact same process that we used on the prior example. So basically taking that vertex that we can see from the graph, using a point, another point on the graph, and then you do have to make an assumption. You have to either assume that you want to make it a vertical stretch or compression or a horizontal one. It's typically easier to describe it using a vertical one. And, in other words, trying to find A instead. And then simply just plugging in that extra point and the vertex into that general vertex form and solving for A or for B if you've decided to create your equation using a horizontal stretch or compression. So that's the process, and see you in class.